In the vast landscape of scientific exploration, the 19th century witnessed a groundbreaking discovery: semiconductors. These peculiar materials, neither perfect conductors nor insulators, possessed unique properties that would shape the future of technology. Michael Faraday observed the intriguing behavior of silver sulfide. He found its conductivity increased with temperature, unlike metals. This marked an early step towards understanding semiconductors. In 1899, Jagadish Chandra Bose made another significant contribution. Bose's experiments with galena demonstrated its ability to detect radio waves. This laid the foundation for crystal radio receivers, precursors to modern wireless communication. These findings hinted at the immense potential of semiconductors, sparking further research. The year 1947 marked a watershed moment in technological history, with the invention of the transistor at Bell Laboratories. This groundbreaking device, developed by John Bardeen, Walter Brattain, and William Shockley, revolutionized the world of electronics. The transistor, a smaller, more efficient, and reliable alternative to bulky vacuum tubes, could amplify and switch electronic signals. This revolutionary invention earned the trio the Nobel Prize in Physics in 1956 and transformed the landscape of electronics. The transistor's small size, low power consumption, and durability made it ideal for a wide range of applications. From portable radios to early computers, the transistor rapidly replaced vacuum tubes, shrinking electronic devices and increasing their capabilities. The invention of the transistor marked the dawn of a new era, the age of miniaturization and integrated circuits. As transistors began to replace vacuum tubes, a new challenge arose: connecting numerous transistors to create complex circuits. This challenge led to the development of the integrated circuit, a pivotal innovation that further revolutionized electronics. In the late 1950s, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently developed methods for creating multiple transistors on a single semiconductor chip. Kilby's first integrated circuit, a crude but functional oscillator, demonstrated the feasibility of integrating multiple electronic components on a single chip. Noyce's approach, using silicon and a planar process, proved more practical for mass production. These innovations led to the development of smaller, faster, and more powerful electronic devices. The integrated circuit paved the way for the microchip, the heart of modern electronics, and the exponential growth of computing power. Section 4. Silicon Valley, the hub of innovation. The advent of the transistor and integrated circuit sparked a technological revolution, and at its epicenter emerged Silicon Valley. This region in California became a hotbed for semiconductor companies, attracting brilliant minds and venture capitalists eager to be part of the burgeoning industry. Companies like Fairchild Semiconductor, Intel, and AMD established themselves in the area, fostering innovation and competition. Intel's invention of the microprocessor in 1971, a single-chip central processing unit, further cemented Silicon Valley's status as the global center for semiconductor innovation. The microprocessor, a miniaturized brain for electronic devices, powered the rise of personal computers and ushered in the digital age. Silicon Valley became synonymous with technological advancement, a testament to the transformative power of semiconductors. Section 5. Semiconductors in the digital age powering modern devices. Today, semiconductors are ubiquitous, powering virtually every aspect of our digital lives. From smartphones and laptops to cars and airplanes, these tiny chips have become the invisible engines driving the modern world. The rapid miniaturization of transistors following Moore's law has led to an exponential increase in computing power, enabling the creation of incredibly sophisticated and compact devices. The impact of semiconductors on communication, entertainment, healthcare, and countless other industries is undeniable. They have revolutionized the way we live, work, and interact with the world. The continuous advancement of semiconductor technology promises even more powerful and versatile devices, opening up new possibilities in artificial intelligence, robotics, and beyond. Section 6. The Future of Semiconductors, Challenges, and Opportunities. As we delve deeper into the digital age, the demand for powerful semiconductors grows. The industry faces significant challenges. Miniaturization of transistors is nearing physical limits, requiring new materials. The complexity and cost of chip fabrication are increasing. Despite these, the future remains bright. New materials like graphene and carbon nanotubes offer potential. Quantum computing presents another exciting avenue. The industry evolves, driven by demand for faster, smaller, and more powerful devices.